This is the biggest colored map display in Minecraft, spanning an area of more than 256 by 256 blocks, while using millions of redstone components. It's more than 15 times faster than my previous display, while still supporting 16 colors and a full 128p resolution. But that's not all. There are even more mind-blowing features I'll reveal later in the video. This project was way outside my comfort zone, since it required me to learn coding. But thanks to today's sponsor Brilliant, learning Python was made easy for me, and the hardest part of this project were the hundreds of hours of designing and testing the display. After finishing my last display, which I mostly just built to see if Minecraft could handle it, I wanted to make a better and faster display for potential future projects. So I started looking at ways to make a color display for a 1:2 scale map. This makes more space available for redstone components, since 1 pixel on a 1:2 map is 2 by 2 blocks. The disadvantage is that you need 4 players holding a map or 1 player that's constantly moving to load the entire map. The color of a pixel on a 1:2 map will be determined by the most prevalent color. If all of the blocks are different, the northwest corner block will be represented on the map. So, if we make a big roof with 3 different blocks and no block on the northwest corner, we can change the pixel on the map by just changing 1 block. The most obvious way to do this is by using pistons. I put 16 pistons above each other, each with a different colored block in front. The piston pushes the block under the hole in the roof, changing the pixel on the map. However, I quickly ran into issues. After hours of designing a row of pixel, I wanted to put several rows together to test. This revealed a big problem. The pixel on the map shows whatever block is below the hole in the roof, meaning nothing can be built there. With this design, the pistons are below the hole in the next row. First, I thought I could just stack the modules, so even though the piston is below the gap, the blocks we change will be above them. But since the map is 128 pixels wide, stacking 128 modules exceeds the build height limit. And that was only the first of many problems I would encounter in this project. Later on, the problems became even harder to notice and solve. That's why I'm happy today's sponsor is Brilliant. Thanks to Brilliant, I was able to write a crucial Python program to finish this project. I'd done a little bit of coding years back in school, but the way it was taught wasn't very interesting or engaging. Even though I wanted to learn more, I never did. Brilliant changed that for me. With their interactive lessons, their first principles approach helps you build an understanding from the ground up. Each lesson is filled with hands-on problem solving that lets you play with concepts. A method proven to be 6 times more effective than watching lecture videos. It helps build your problem solving skills through active learning, not memorizing. So, while you're building real knowledge, you're also becoming a better thinker. Brilliant helps you develop a powerful daily learning habit, which is great for personal and professional growth. The fun and bite-sized lessons makes it easy to build real knowledge every day. There are a growing number of courses that are perfect for building a strong foundation and learning real-world applications. To try everything Brilliant have to offer for free for a full 30 days, visit brilliant.org/Mr. Kowalski or click the link in the description. You'll also get 20% off an annual premium subscription. After my first failure, my next idea was to pull the block below the gap instead of pushing it. This made things way harder, because we can only use 1 tick pulses on the piston. And before changing to a new color, we need to activate the old color again to push it back. This meant we would need to store the color of more than 16,000 pixels and access all of this data before changing a frame. Besides, the same block can have a different color on the map depending on its height compared to the pixel next to it. Different colors have different heights in this setup, making the same color appear different if there is another color next to it. I couldn't find a solution to this problem and worked on some more ideas, but things got more and more complex and performance hungry. That's when I remembered an idea Magic showed me a while back. His idea was to use shulker boxes as pixels on a 1x1 map. My first map display used concrete powder pushed by pistons on a 1x1 map, which was a performance disaster. But I liked the idea and I wanted to see if Minecraft could handle an entire map. So, I tried to get a 1x1 map working using shulkers, but I couldn't find a way to quickly deliver the correct shulkers to the dispensers. On a 2x2 map, 3/4 of the area on the map can be used to build. Transparent blocks like glass are not visible on the map. So, I can place a glass block with redstone or repeaters on top and it will still show the block below. This was very useful later in the build. Here's my first shulker map display prototype. I quickly threw it together to see if the idea was viable at all. And it worked very well. To send a shulker to every pixel, I used instant droppers. They can instantly send an item from one location to another using instant wires. So, I can store all the different colors of shulkers on one side and then send them to specific points along the instant dropper by activating the instant dropper at different places. The item will always travel one block further than the point of activation on the dropper line. At first I just used one color of shulker to test the rest of the system. It takes about 52 seconds to send a shulker to every pixel. You can immediately place the shulkers to draw a new frame in under a minute. This is already much faster than my previous display, which took about 15 minutes for one frame. But that's not all. This display will have a special feature. You can preload frames. Since there is a barrel above the dispenser, you can first load shulkers into the storage and then refresh an entire frame at once. The first test of preloaded frames went very well. Even though the game was lagging and each frame change took more than 10 seconds instead of less than 1, I was very happy with this result, since seeing an entire map change in just 10 seconds using only redstone was very promising. But I thought I could still improve performance and add some features, so I made a new version where I doubled the amount of preloaded frames to 54. But the performance was significantly worse, so I had to scrap that version and begin on another one, focusing on performance. I significantly reduced the lag a pixel creates when changing. On the left is a pixel from version 1 and version 2, and on the right is the final version. I removed 4 moving blocks, and there are fewer redstone components activated when updating pixels. Now the piston directly breaks the shulker. At the same time, a dropper unlocks and gets unlocked again to pick it up. All hoppers in this display are always locked, and only unlocked for the ticks when they are needed. This is done to reduce lag. I managed to bring the time for a frame change down to 6 seconds, which means the game is still lagging, but it's better than the first version. Just preloading one or multiple frames doesn't really make this a display yet. We need to be able to control pixels individually, without having to refresh the entire frame. Map shading only looks at the blocks above or below on the map. So by building the row from the north to south, every pixel in that row is at the same height. The next row can be on another height, as long as there are no blocks above the shulkers. Dividing the rows into 4 groups on different heights gives each row an 8x2 area for each pixel, and also enough space to control the color later on. To update a single pixel, we need to send one signal to the specific location of the pixel, and a second one to put a shulker into the instant line. To select the pixel, I made this binary decoder. You can input a binary number and it will send a signal to the corresponding output. This binary decoder is quite large because it couldn't be wider than 8 blocks, but more importantly, it doesn't obstruct the pixels below and doesn't generate lots of lag. Each of the 128 rows has its own binary decoder, allowing us to change up to 128 pixels at a time. So if you just want to write some text or need to change just a few pixels, you can do that. After some testing, all the pixels were working as they should. And the next project was the shulker storage, which stores all the different colors. To select specific colors, I used my music disc reader, which I already successfully used for my previous display. As input, it takes shulkers filled with music disk. The music disk enters the jukebox, which outputs a unique signal strength for each disk. That way, each slot in the shulker can store 16 different values. By assigning a color to each signal strength, each music disk represents a color. To store the value of each pixel in a row, we need 5 shulkers, and 640 shulkers in total to store the data for an entire frame. This makes the data storage 27 times more compact compared to just storing the different colored shulkers in chests. Since things got bigger and bigger, it was really useful to know how new parts affect performance. So, I wrote a simple program in Python. This program plotted the time it took to load shulkers into the display and the time it took to change a frame into a graph. This allowed me to easily see how new additions impacted performance, and I could compare the performance against previous versions. Here you can see a graph of simply loading one color of shulkers from a chest versus using all the disk readers. My last display used 32 disk readers, and now I'm using 128. Connecting the readers to all 128 rows was more work than I anticipated. Many failed tests and lots of troubleshooting later, all disk readers were connected and able to send shulkers to the display. To test them, I used shulkers filled with disks that would count up from signal strength 0 to 15. This way every color is tested and issues are clearly visible. I was very happy after the first successful test with all the disk readers, as that meant the display was working. But to show an actual image, I needed to find a way to translate an image into shulkers filled with music disk. For my previous display, I built a scanner that would detect and store the corresponding music disk. But this took almost 30 minutes per image. I needed a more efficient solution. There wasn't a program available that could convert an image into items stored in chests, so I decided to create my own. There are already programs that can convert images into schematics containing blocks. So I could parse the data from that schematic using Python into a schematic containing barrels in the right locations, which contain shulkers filled with music disks corresponding to the pixels of the image. This greatly reduced the time required to prepare images for the display. Finally, it was time to test the display with actual images.
Alright, it's done. Okay. Once. Twice. Yes!
I loaded in some more images and this is how it looks. This is already awesome. You can load multiple images and quickly show them just using Redstone. But the next thing I will show you is what makes this display truly special. This is how it would look if Minecraft would run at normal speed. The fastest you can refresh preloaded images is every 4 redstone ticks, which is 2.5 FPS. This is 2 FPS. Yes, that's true. This display can actually play GIFs and short clips just using Redstone. No mods, no command blocks. This absolutely blows my mind. This is already way more than I would have ever thought possible when starting this project. There are so many epic things I can do with this. So if you want to see that, subscribe to my channel. I learned a lot from this project, and I hope I can inspire you to go outside your comfort zone and start a project you don't have the knowledge or skills for yet. Thanks a lot for watching. If you enjoyed this video, go watch the video from my previous display, then you can see how much of an improvement this one is.